Hello and welcome. UVA Speaks is a podcast of Lifetime Learning, a division of the Office of Engagement at the University of Virginia. Lifetime Learning brings the knowledge and expertise of UVA's faculty to the university's alumni, friends, and families. My name is Susan Lynch, and I am the Associate Director of Lifetime Learning at the University of Virginia's Office of Engagement. This podcast features Nicole Long, an assistant professor of psychology in the Department of Psychology at the College and Graduate School of Arts and Sciences at the University of Virginia. Long teaches in the psychology department and is a researcher at the Virginia Alzheimer's Disease Center and principal investigator in long-term memory lab. Through her research, she aims to understand how we use strategic, goal-directed processes to form and retrieve memories. In this podcast, Professor Long will talk with us about her research with the Long-Term Memory Lab. So thank you, Professor, for speaking with me today.
You're welcome. Thank you so much for having me.
Great. So first, before we talk about the research that your lab conducts, your expertise is within the field of cognitive neuroscience. So can you explain what is cognitive neuroscience?
Sure. So the textbook definition is it's how the brain gives rise to the mind. But explicitly what it is an interdisciplinary field that draws actually on a lot of different fields, but in particular, neuroscience and psychology. And I really see it kind of as the bridge between the two. So you'll often hear like cute quotes like bench to bedside. Well, the bench is neuroscience. The bedside would be more on the psychology side. How do you get from one to the other? Cogneuro, at least when you're talking about the brain. So ultimately, cognitive neuroscience is a basic science where we're trying to understand just how the brain functions, and in particular, how those functions support cognitive processes like memory, attention, decision-making, language, without necessarily trying to develop treatments for diseases or clinical interventions, but the idea being that once we have a full picture of how the brain supports those things like memory, we can then, people with more kind of clinical backgrounds can take that information to develop either effective treatments or interventions for when those processes go awry. So ultimately, cognitive neuroscience is trying to suss out what brain mechanisms go with what cognitive processes so that we can understand how the brain works.
Okay, great. Thank you. So what kind of laboratory tasks do cognitive neuroscientists conduct, and how do you record brain signals?
Yes. So our laboratory tasks are actually kind of deceptively simple. So if you were going to be a participant in my lab, you would come into my lab space, sit in front of a computer, and do basically a very boring computer game. Some cognitive neuroscientists use more exciting games with like virtual reality and more kind of real world things. But in my lab, we use a lot of kind of bread and butter tasks like I give you a list of random words and ask you to memorize them. And then later I test you on your memory for those words. So that's where we kind of draw on the psychology aspect, where we use very, very kind of heavily controlled tasks so that we can really zoom in and focus on specific cognitive processes and really even like processes within processes, because everybody will be like, oh, well, I mean, no one memorizes a list of words in the real world. It's like, of course not. No, but everything you do in the real world is so complicated and so layered that in the lab, what we do is try to pare things down to like the simplest, we're trying to get to the atom of cognitive processing. So we use these heavily controlled laboratory tasks so we can really kind of tease apart how is your brain responding for this condition versus that. So if I give you a list of words to remember versus a list of pictures to remember, like what is your brain doing differently in those two cases? And that brings us to the recording part, which is the fun part of cognitive neuroscience is everything we do is non-invasive. So no one's getting surgeries, no one's getting implants. It's all someone comes into a lab, they sit in front of a computer, or maybe they lay in a magnetic resonance imaging machine and look at pictures projected above their face. They do these tasks while we record either electrical signals from a swim cap that's fitted with sensors, or we take photographs of the brain through an MRI machine. And the real kind of strength of cognitive neuroscience is that we are measuring the function of the brain while it is engaging in those functions. So in In a clinical setting, I mean, many people have had MRIs for health related reasons. Most of that is trying to figure out structure. So if there's a broken bone or if there's some sort of brain change that's happened as a result of, say, an injury, we are actually measuring not just structure, but also function. So how is your brain responding moment to moment to moment when I show you that list of words, when you try to remember those words, etc. And we're really looking mostly, there are some cases where we're very, very kind of fine grained detail, but usually we're looking kind of at the brain as a whole and how different areas or parts of the brain are responding, again, on the order of either milliseconds or a couple of seconds, as opposed to kind of more long-term measurements.
Okay, interesting. So, what has cognitive neuroscience uncovered about how the brain supports memory?
Yeah, so cognitive neuroscience is a broad field with a lot of domains. Basically, if you're a cognitive neuroscientist, you probably specialize in one of those processes I talked about. So, memory, attention, decision making, language, there are others. So, my kind of key focus is on memory. And cognitive neuroscience has been kind of instrumental in our understanding of memory processes for one like very key reason that I think seems obvious after you talk about it, but isn't necessarily something one thinks about up front, which is imagine you meet someone on Zoom and you learn that her name is Nicole. And then later you run into this person at a grocery store and you're like, who, oh yes, I've met that person. Her name is Nicole. Those were two separate processes and two separate kind of obviously moments in time. At the first instance on Zoom, you had to form a memory or create a link or association between my name, Nicole, and my face and other details about me. And then at the grocery store, you had to access that information. So in the lab, we would call that the study phase and the test phase. And the really kind of both interesting and tricky thing about memory is if you remember something, you had to have both formed or encoded that memory and you have to have accessed or retrieved the memory. But if you forget something, why did you forget it? Did you forget it because you never formed that memory in the first place? You know, you were distracted, you weren't paying attention, something else. Or when you see someone at the grocery store and you're like, I know I've met this person before, but I can't remember her name. Is it there in your brain, but it's just not available to you? So maybe you could access it, but for whatever reason, you know, Zoom and grocery stores are totally different contexts. So maybe if you'd seen me on Zoom a second time, then it'd be like, oh, that's Nicole. So the fundamental problem with just relying on behavior for understanding memory is that behaviorally, I get one measurement. Did you remember yes or no? But there were at least two things that had to happen. So we can't suss out from behavior alone what people are doing in kind of both of those points at the encoding and the retrieval. So a lot of cognitive neuroscience memory research has been focused on both kind of separately investigating those 2 points and in particular measuring brains while people are studying information to see, are there differences in your brain when you are first encountering something that will then later predict what you will and what you won't remember? And I mean, again, intuitively, it seems like there should be things in the brain, and there are, but without cognitive neuroscience, we wouldn't know what any of those things are or kind of when they're operating and what they might be doing. So obviously a comparison of remembered and forgotten is kind of a blunt tool because again, you can forget things for a lot of different reasons. But what we've been able to do in cognitive neuroscience using our very kind of artificial but heavily controlled laboratory tasks is really get into, well, not just what do you remember, but how are you remembering things? Are you remembering, if I give you that list of words, are you remembering not just how many are you remembering, but are you remembering them maybe in the order I presented them in? Are you remembering maybe words that are related to each other? So if I give you a list of words and the word dog and cat are somewhere on there, you're probably going to remember them together if you do remember them. So what's the brain doing that allows you to actually engage in this kind of very detail rich, like associative structure of your memory? And what Cogneuro has shown us is that there are, of course, multiple different brain regions involved. They're involved at different times. And we're still really just kind of learning what all of these different mechanisms are, how they work together, with the ultimate goal being, if you actually know what the brain kind of should look like optimally in order to successfully form a memory, then in theory, you can perturb the brain to put it into that state so that you can then help people remember if they're either not effectively encoding in the current moment or maybe on longer timescales. So again, that's where we come back to the bench to bedside, which if we know the basic mechanisms of how memory is kind of typically operating in the brain, we can then start to figure out, well, what happens when it goes wrong?
Okay, great. So this question gets to some of the detail then. So your lab's research program is focused on understanding the processes that support memory encoding and memory retrieval, as you mentioned, using machine learning methods and brain data. Can you take us through what your work has shown?
Yeah. So what I described in terms of cognitive neuroscience research in the prior question was a lot of kind of the initial work that had been done in the field that was really trying to kind of divide and conquer and really reduce things to the simplest aspect possible. And I mean, that's important because the brain is a very complicated organ and it's necessary to in order to make kind of solving these problems tractable, we need to kind of subdivide. And kind of in conjunction with that, cognitive neuroscience is a very young field. So the term was coined in like the 60s or 70s, but it only really got going kind of in full force in like the 1990s with the advent of fMRI, functional magnetic resonance imaging. So a lot of the early work in the last few decades has been really this like parcellating out of like, can we figure out which very specific processes are associated with very particular brain areas and kind of doing these very kind of fine-grained comparisons to figure out, well, is this brain area more active for, pictures versus words? And that has been a great foundation for kind of getting us started in, okay, where are we looking? What kind of paradigms can we use? That sort of thing. But it obviously misses the fact that your brain works entirely like all together at once. So a lot of research, including the work done in my lab in recent years, is trying to kind of zoom out a bit and focus not just on kind of the individual pieces of kind of different cognitive processes in different parts of the brain, but really take kind of what would be called a network-based approach or like a whole brain approach of assessing not just kind of what are the individual pieces, but can we start to distinguish when you're engaging in these processes kind of moment to moment? So my lab is really focused on understanding encoding versus retrieval. So again, intuitively, like those feel like different things. So one of the questions we started with was, well, can we use machine learning approaches to determine or decode which brain state encoding or retrieval you might be in? And so we consider those as brain states because as kind of like a collection of processes. So if I ask you to retrieve, what did you have for breakfast yesterday? There's a lot that goes on with that, right? Because first of all, you have to do the perceptual processing of figuring out what those words mean, what they connect to. Then you need to start doing some sort of kind of search process. You probably would do something where you'd imagine yourself at your kitchen table. You probably also access information of like, well, I always have muffins every day. So that would probably pop to mind pretty automatically. Then you'd have several choices to select from. And then you'd be like, okay, well, yesterday I'd been bored with muffins, so I decided to have just, a couple of bananas. And then you have to actually make a response and report that. All of that kind of fits under the rubric of retrieval. So there's lots of these different kind of pieces to that overarching idea. So we consider kind of memory retrieval as this broad brain state that involves multiple processes and multiple different brain areas. So kind of our first question had been, well, can we actually just distinguish encoding from retrieval? So we use machine learning where we train an algorithm based on a set of brain activity or brain patterns. Here's what the brain looks like when we've told a bunch of people to try to encode things. Here's what the brain looks like when we've told a bunch of people to try to retrieve things, or the same people. We always do it within participants. Now we give the algorithm a new set of data that it's never seen before, and we say, what do you think is happening here? Do you think does this look like encoding or does it look like retrieval? And we, the experimenters, know what it's supposed to be. So if the brain reliably distinguishes and has kind of different networks involved, then what we should find is that the algorithm is like, that looks like retrieval. And we go and look, what was it actually? It was retrieval. then that tells us that we can use these kind of distributed patterns of brain activity to tell apart whether someone is encoding or retrieving. That's the first question. So you have to do that first before anything else, because if you can't tell them apart, then everything else I'm about to say doesn't make any sense. But that was kind of like where we started. But ultimately, what we're really interested in is like, okay, well, then how do you engage these states? How do you maintain them? What are the consequences for how you're kind of interacting with the world based on which of these brain states you might be in? So that's kind of the main research direction in my lab currently, where we're trying to understand, okay, how much do you kind of just slip into a retrieval state? And how is that kind of driven by things that have happened recently, or kind of relatedness between experiences? So I gave the example before of you meet someone on Zoom, you see them at the grocery store. Well, presumably, if you see me at the grocery store tomorrow, that's probably going to lead to a lot of like you're going to immediately go into this zone of like, oh yes, I've seen that person before, kind of bringing back to mind a lot of our conversation today. So what we've shown is that you're much more likely to engage in this retrieval state when kind of the two experiences that you have are really overlapping in time. And we think that that would happen in a lot of different scenarios, where if there are similar kind of meaning or semantic relatedness between experiences. So I gave the example before that it might be hard to remember my name at a grocery store, but the other idea would be if you see me again, but maybe it's in 2 years, but it's on Zoom, then that relatedness is also going to really help you kind of engage this internal state of trying to retrieve. But if you want to be forming a new memory about something that's going on currently, our research and others that our work is based on suggests that engaging in retrieval can be maladaptive or detrimental. So the kind of basic premise is that you can't be doing encoding and retrieval at exactly the same moment, because they rely on kind of different configurations of the same brain circuitry. So they kind of tap into similar things, but it's kind of like one switch is on and one switch is off, and they can't both be in the same state at the same time. So what that means is you might kind of have a tendency to engage in retrieval based on kind of these relatedness or overlapping experiences. But if, again, you run into me at the grocery store and I'm telling you, you shouldn't buy these apples because they're not good quality or something. If you're spending that time trying to retrieve and remember what my name is, you're not encoding the new information I've just given you. And then later, if someone tests you on your memory for the apple quality, i.e., did you end up buying them? Your memory for that experience will be worse. So what we think is happening is that there's this very complex interplay of like how your goals are informing what states you're engaging in, but then how the world is kind of pushing you into states. And we think that these states change as we age. So there's a lot of literature that even if we're healthy as we age, our memories kind of decline in very kind of particular ways as opposed to just generally. And we have one of our hypotheses is that some of those declines might be related to kind of your ability to selectively engage in these particular states, as well as your ability to engage in ones you want to engage and disengage the ones that are not really what you want for your current goals. And what we've also found is that I've been calling these encoding and retrieval states. They actually seem to be involved in those other domains, even when there is no really memory demand. So we've run a few attention tasks where there's nothing, we're not asking people to remember who they met on Zoom or what they had for breakfast or anything like that. It's really just like detecting arrows and directions, very, very basic level. Like, did you see this thing I just presented? And what we find is that what we've been measuring as the retrieval state can also be engaged in that kind of a task. So what that really suggests is that this might be something even bigger than just memory itself, where it's more this like how you are orienting your attention. And again, we know kind of intuitively from real life that if you're not focusing your attention in one way, you're missing whatever it is you're not focusing your attention on. So we're really interested in, again, kind of measuring how these states are engaged, both kind of in terms of the control you can exert on them, as well as what the world is making you do, and then what kind of consequences that has for kind of all of your different cognitive behaviors.
Wow, great. Thank you so much for all of that. So, and finally, this is the big question. What strategies can people use to avoid forgetting? I mean, we would all like to know some.
Yes. So that is definitely the number one question I'm always asked as soon as somebody finds out I do memory research. And my number one answer is always forgetting is normal. We are meant to forget. If you think about every experience you have moment to moment, day to day, like I always give the what you have for breakfast example. Do you need to remember distinctly every single day you've had breakfast? No. Like if you think like what is going to help you survive, you need to remember what breakfast did you have that you like to eat and, makes you healthy. And if you ever have something for breakfast that makes you ill, then you need to remember that. But otherwise, if it's I'm just having muffins every single day, you don't need to remember all of those experiences, and it can help the efficiency of your memory to not have kind of all of those other pieces of information kind of basically cluttering things up in terms of like if you do actually need to retrieve something very specific and you have all these other competing memories, that makes it very, very difficult. So the number one thing is we are supposed to forget. But obviously, there are always things where we do actually really want to remember them. It's not what we've had for breakfast every day, and we just don't. So what can we do to make that better? Well, there's no silver bullet. There's no one thing that you do it's going to work. But there are lots of strategies that generally are like, will help you and will make things more effective. And it's pretty much all the things that you would already intuitively think of. So if you want to remember something, one of the best ways to do it is to pay attention. So when I meet people, invariably everybody always says, "Oh, I'm bad with names." And I'm like, "Well, everybody's bad with names." And there's very clear reasons why, in that names and faces, there's no like real rationale for why my face doesn't mean Nicole. Like, there's no way you would just see my face and you would automatically be like, oh, yes, that looks like a Nicole. We usually start to think that after we've learned somebody's name, then we'll start to make those associations. But like initially, there's no reason that a name should go with a face. So that means that we're already kind of at a disadvantage there. The other element is, in the case of learning names and faces, is especially as we've gone through the world and we learn the process of being introduced to people, we stop paying attention because it becomes automatic, where it's like, yeah, someone's going to come up to you, you're not going to recognize them. So the procedure that's going to happen is going to be like a handshake or something like that. And they're going to say their name and you're going to say your name. And you could probably do all of that completely on autopilot. You're probably spending, I would guess, I don't actually know if this is true, but my hunch would be you're spending more time kind of preparing for introducing yourself as opposed to waiting to listen to the other person, because there's obviously like social consequences and things like that. So what you can do is be like, tell yourself, I'm really going to focus on what this person is saying in this moment in time. And I'm pretty sure this is like a strategy people say in like the business world, like repeat the person's name back to them, because that makes you process it again and process it differently. So that's one of the other big things, which is processing things repeatedly in different ways is going to be helpful at kind of stabilizing that memory. So being really focused on it in the moment and then bringing it back sometime later. So in the classroom, I'm always telling students, you need to practice studying. So it's not just wait before the exam, but it's also practice retrieving it, because that's what you're ultimately going to do. So not just like rereading something, but trying to engage in it in a different way, particularly trying to engage that retrieval process, because potentially what's happening is you are practicing the action of engaging a retrieval state, and such that when you actually need that state again for the test or whenever you actually need to retrieve that memory, you've already kind of practiced that process and it's easier and more likely to be successful. So it's all those kind of little things of paying attention, trying to link things in different ways, trying to experience things in different ways, that ultimately is going to boost the chances of remembering. It's never going to be, you can use all of these strategies and still forget things. And the other thing is, everything I've just described is very resource intensive. You can't do all of those things like every single second for your entire life. Like your brain will run out of juice. You will be so hungry because it will have burned through all of your fuel. So you can't deploy it all the time. So another thing is like being very selective. And again, like acknowledging there are some things that are worth forgetting and you're not going to exert energy on those. So you're going to reserve your resources for those really critical moments and be like, identify, okay, this is a time where I really need to be focused. And I'm going to engage in kind of all of these advanced processes to try to really make that stuff stick.
Yeah, I think in today's culture, we're always trying to go one step ahead. So slow down, pay attention.
Yes.
And that's very good advice. So, well, wonderful. Well, thank you so much, Professor, for sharing all this information about your lab and your research. I'm sure that many people will appreciate hearing about your findings and about their own health and their own memory and that of their families. We're always paying attention to ourselves and our families and how our family members are doing in this regard. And I think this will help us give some information to think about as we do that. So thank you again. And I appreciate you sharing your knowledge and expertise with UVA's alumni, friends, and families.
Yes, you're welcome. Thank you so much for having me.
Great. Thank you. And thank you so much to everybody for listening. For upcoming podcasts and other Lifetime Learning programming, recordings, and blogs, please visit our website at engagement.virginia.edu/learn. You can also find our podcasts on the Virginia Audio Collective, which is a network of UVA podcasts hosted by WTJU Radio and can be found at the virginiaaudio.org. So thanks again, and we look forward to you taking part in future Lifetime Learning programs.